Following are the reagents used for allylic substitution. Allylic substitution means substitution of allylic hydrogen by halogen. But for competitive examination, always remember, all these reagents result in substitution of allylic hydrogen and tertiary hydrogen by halogen. Cl2 at 773 Kelvin and SO2Cl2, that is sulfuryl chloride, result in chlorination, and Br2 773 Kelvin and NBS result in bromination. Allylic substitution means replacement of allylic hydrogen by halogen. Carbon next to the double bond is called as allylic carbon, and hydrogen attached to this carbon is called as allylic hydrogen. This reactant can be represented as, now this separated hydrogen is allylic hydrogen. So all these reagent replaces this hydrogen by halogen. Halogen can be chlorine or bromine. So let's understand their reaction one by one. First of all, chlorination. Cl2 at 773 Kelvin, reaction takes place as allylic hydrogen from alkene and halogen from Cl2 separates as HCl. The remaining halogen occupy the position of allylic hydrogen to give allyl chloride, SO2Cl2, that is sulfuryl chloride. Reaction takes place as allylic hydrogen and chlorine separates as HCl, SO2 separates as sulfur dioxide, and remaining chlorine occupies the position of allylic hydrogen. Out of these two methods, the method of SO2Cl2 is preferable because the byproduct formed during this reaction, that is HCl and SO2, are gaseous and are removed from reaction mixture by evaporation. Hence, we get pure allyl halide. Bromination, that is replacement of allylic hydrogen by bromine. First reagent is Br2 at 773 Kelvin. Reaction takes place in similar manner as that of Cl2 773 Kelvin. That is, allylic hydrogen and bromine separates as HBr and remaining bromine occupies the position of allylic hydrogen to give allyl bromide. Next reagent is NBS, that is N-bromosuccinimide. The function of this reagent is same, that is replacement of allylic hydrogen by bromine. So you can directly write the reaction of NBS. So we get allyl bromide. Out of these two reagents, we prefer NBS because it is better yielding method for bromination at allylic position. The other function of NBS are allylic substitution on alkene as well as acid chloride. For example, in this reaction, NBS replaces allylic hydrogen by bromine, so allylic substitution on alkene. In the second reaction, NBS also reacts on acid chloride and replaces alpha hydrogen, that is, carbon next to the functional group is called as alpha carbon and its hydrogen are called as alpha hydrogen. So NBS replaces alpha hydrogen of acid chloride by bromine. So these are the two functions of NBS for your competitive examinations. Ozonolysis may be defined as reductive cleavage of alkene or alkyne in presence of ozone to give aldehyde or ketone. So during this reaction, alkene and alkyne form aldehyde or ketone. Reaction takes place as ozone in solvent like CH2Cl2 reacts with alkene. Splitting of two bonds at the site of pi bond takes place, and this results in formation of ozonite as the species formed by ozone is called as ozonite. This ozonite on reaction with zinc form aldehyde or ketone. In this case, only aldehydes are formed. Splitting of peroxide linkage takes place as, and after completion of valency, we get two aldehydes. They can be written as ethanol and methanol. Ozonolysis reaction can be represented in one step as alkene reacts with ozone, zinc and water. So in one step we replace pi bond and other bond at the site of pi bond with double bond oxygen. So these two bonds at the site of pi bond are replaced by double bond oxygen. So final product is we get left hand side aldehyde and right hand side ketone. So this carbon oxygen double bond is formed at the place of pi bond. Similarly, this bond is also formed at the place of pi bond. Importance of ozonolysis. By ozonolysis product, we can identify parent alkene. Let's understand with the help of one example. An alkene A give following compound on ozonolysis. Predict the structure of parent alkene. Compound forms are ethanol and acetone. So this problem can be solved as write both the product of ozonolysis in a sequence as they are given. First is ethanol and second is acetone. Write both the molecule in such a manner that their oxygen face towards each other. Now, remove the oxygen and extend the multiple bond to form alkene. So the parent alkene is this final alkene which gave ethanol and acetone as ozonolysis product. Let's take one more example. An alkene A gave ethanol, ethanediol and methanol. So writing all the compounds in a sequence as given, first ethanol, then ethanediol, then methanol. Write them in such a manner that oxygen points towards each other. Now remove the oxygen and extend the multiple bond to get alkene. So in this way, we can understand the entire concept of ozonolysis. Let's understand the reaction between benzene, halogen, that is chlorine, in presence of anhydrous AlCl3. Instead of anhydrous AlCl3, we can take anhydrous FeCl3. Splitting takes place as hydrogen from benzene ring and halogen from adding agent are removed as halogen acid HCl, and the remaining part occupy the position on benzene ring to form chlorobenzene. In this reaction, halogen is substituting on benzene ring, so the reaction is called as halogenation reaction. In second reaction, benzene reacts with alkyl halide. As in this case, the reacting species is methyl chloride. Splittings are same: hydrogen from the ring, halogen from the alkyl halide, and remaining part, that is alkyl group, on benzene ring. So this reaction is called as alkylation reaction, and it is also called as Friedel-Crafts alkylation reaction. The next reaction is reaction of benzene with acid chloride. In this case, it is ethanoyl chloride. Splittings are same: hydrogen from the ring, halogen from the adding agent, removed as HCl, and the remaining part on benzene ring to form acetophenone. The attached species is acyl group or acetyl group, and that is why the reaction is called as acylation reaction or acetylation reaction. It is also known as Friedel-Crafts acylation or Friedel-Crafts acetylation reaction. Acylation reaction can be shown with the help of acid anhydride, benzene with acetic anhydride. Splittings are hydrogen from benzene and acetate part from the adding reactant. Splitting of acetic acid, remaining part on benzene ring, hence we get acetophenone. Again the reaction is acylation or acetylation and is also called as Friedel-Crafts acylation or Friedel-Crafts acetylation. So students, remember, two acetylating agents are ethanoyl chloride and acetic anhydride. We prefer acetic anhydride because reactivity of ethanoyl chloride is very high and we cannot control reaction of ethanoyl chloride. So better acetylating agent is acetic anhydride. So let's understand the mechanism of halogenation. Mechanism of halogenation and Friedel-Crafts alkylation and acylation is same. So let's understand the mechanism of this reaction. Reaction starts with splitting of Cl2 or any other reagents which we take during this reaction. Heterolytic bond fission result in the formation of cation and anion. Anhydrous AlCl3 gains anion and in this way act as halogen carrier. So for competitive examination, the function of AlCl3 is it acts as halogen carrier. The remaining Cl positive ion attacks on benzene ring. So we can say the attacking species is positively charged electrophile. So the reaction is electrophilic substitution reaction. So after addition on benzene ring, positive charge at ortho position. Now resonance takes place. This results in positive charge at para position. Again on resonance, positive charge on ortho position. Now from this last structure, deprotonation takes place, that is removal of proton. Removal of proton result in formation of pi bond S and we get final product chlorobenzene. Nitration reaction. Nitration on benzene takes place in presence of mixture of concentrated nitric acid and concentrated sulfuric acid. The mixture of concentrated nitric acid and sulfuric acid is called as nitrating mixture. Splittings are hydrogen from the ring, OH from nitric acid removed as water, the remaining part on benzene ring to form nitrobenzene. Mechanism can be represented as, first of all, sulfuric acid splits as proton and HSO4 negative ion. Nitric acid accepts this proton to form positively charged species. Since H2SO4 is losing proton, so it is acting like as an acid, whereas nitric acid gains proton, so it acts as base. So HNO3 acts as base during nitration reaction and H2SO4 acts as acid. The final species formed is NO2 positive, which is also called as nitronium ion. So again we can represent it as nitronium ion, which is attacking species. So till now, remember, H2SO4 is an acid, HNO3 is a base, and attacking species is NO2 positive. reaction takes place as splitting of pi bond on benzene ring, attack of NO2 positive on benzene ring, then resonance. This generates positive charge at para position, again resonance, positive charge at ortho position, then finally deprotonation, that is removal of proton, result in formation of pi bond. So in this manner we get nitrobenzene. Directive influence is the ability of already attached group to direct the incoming group at particular position on benzene ring. For example, reaction on this compound is determined by group X. If group X is plus R, then incoming electrophile will attack on ortho and para position, and if this attached group is minus R, then incoming electrophile will occupy meta position. For example, if we have the reaction chlorobenzene reacts with Cl2. So first of all, see the nature of group attached on benzene ring. The group attached on benzene ring is plus R, hence reaction will take place at ortho and para position, as hydrogen from ortho position and chlorine from incoming Cl2 are removed as HCl, and remaining Cl occupy ortho position. Similar reaction takes place at para position, so we get two compound, one ortho substituted and the second is para substituted. Let's take another example. Now in this case, attached group is aldehyde, which is minus R. So reaction will take place at meta position. So reaction can be represented as hydrogen from meta position and chlorine from adding agent are removed as HCl, and remaining chlorine occupy meta position. So now we can easily understand the meaning of directive influence, the ability of already attached group to direct the incoming group at particular position on benzene ring. Now let's talk about polymerization reaction. It is the process of combining of large number of small molecule to form bigger molecule. So we can say the small molecule combines together to form bigger molecule. The bigger molecule formed is called as polymer, and combining small species are called as monomer. So monomers combines to give polymer. Let's take few examples. First of all, polyolefins. Polyolefins are the polymers of alkene. In this category, first example is polythene. The monomer of polythene is ethene. Reaction can be represented as N molecule of ethene in presence of catalyst, generally Ziegler-Natta catalyst. Reaction can be represented as the monomer is ethene, hence the polymer is polythene. Polythene is of two types. Number 1, high density polythene HDP, and number 2, low density polythene LDP. First of all, high density polythene. Linear, translucent, chemically inert, and high tensile strength. Can be used for making of containers, pipes, bottles, toys, bags, etc. Second type of polythene is low density polymer or LDP. Can be prepared at 465 to 485 Kelvin at very high pressure of 15 atmosphere. Its properties are branched chain and transparent, chemically inert, moderate tensile strength. Next polymer is polypropylene. The monomer is propene. Reaction can be represented as propene on polymerization in presence of catalyst give polypropylene. Next is polystyrene, monomer styrene. Reaction can be represented as, now the polymer formed is polystyrene. Polystyrene is used for preparation of thermocol. Next category is polyhaloolefins. Means these are the polymers of halogen containing alkenes. First is PVC, polyvinyl chloride. Monomer is vinyl chloride. This vinyl chloride on polymerization give PVC. PVC is used for preparation of various products like pipes, doormats, other pipes, etc. The second example of polyhaloolefins, it is very important example, PTFE. Full form is polytetrafluoroethene. The monomer is tetrafluoroethene, or in short we can say TFE. Tetrafluoroethene on polymerization give polytetrafluoroethene, that is PTFE. The commercial name of PTFE is Teflon, a well-known compound, Teflon. Teflon is heat resistant and pH resistant substance. Now let's understand polymerization in case of alkynes. First of all, ethyne in presence of red hot iron. Now 3 molecules of ethyne reacts to give benzene. Splittings can be represented as 1 molecule, 2nd molecule, 3rd molecule. On heterolytic bond fission, this result in generation of benzene. Second condition is red hot iron on propyne. Reaction takes place to give mesitylene. Splittings are now 3 molecules of propynes, heterolytic bond fission, and this give mesitylene. On ethine, the second catalyst is nickel dicyanide. 4 molecules of ethynes reacts to give cyclooctatetraene. Splittings are 4 molecules, heterolytic bond fission, and then formation of cyclooctatetraene. The last type is action of CuCl, NH4Cl on ethine. In limited quantity, splittings are splitting of pi bond of one compound, migration of hydrogen from first compound to second compound, and then remaining part. The compound formed is called as vinyl acetylene. The IUPAC name of this compound is but1ene3-ine. In excess, reaction takes place as now 3 molecules of ethine reacts with CuCl, NH4Cl. Splittings are splitting of one pi bond of terminal 2 alkenes, hydrogen from central molecule shifts on terminal carbon, and the remaining part is. So the final compound formed is called as divinyl acetylene.